You see what I'm saying? And so it's important to understand that generalization is only possible when we are in non-atomic representations. Right? Okay, and so in the case of reinforcement till now, we basically just try to quickly figure out the value of an atomic state. It's a kind of a learning because you're learning how far you will get starting from this state. So you're in the atomic level, but you're able to learn its value in that space. One of the problems, of course, is the state spaces can be very large. And we started talking about this from the beginning of the course. Even for something like the vacuum world scenario, instead of thinking of them as 8 states, S1 to S8, right? You wanted to think of them in terms of features. Is the vacuum in the left room or the right room? Is there dirt on the floor in the left room, and is there dirt on the floor in the right room? These are features. It's the feature-based representations that will allow you at least to generalize. You may be wrong in generalizing, but you don't have feature-based or what you call non-atomic, or all the names, the synonyms for non-atomic representation. Synonyms are lifted representations, factored representations, feature-based representations. All of these essentially mean you're no longer in atomic worlds anymore, atomic states anymore. Okay? In terms of lifted, you can also talk about relational representations. It's just that feature-based, but it has more like predicate calculus kind of semantics. There are relations between objects. We'll talk about these issues later. But at least you should be able to understand that you could potentially have considered representing states in terms of features. And when you do that, then basically that's the first time you'll start having multiple states having similar features. You can actually talk about similarity of states in terms of that's their representation. Just as you can talk about similarity of people in terms of their features. You know, this person is white, this person is white. This person has long hair, this person has long hair. This person is awake, this person is also awake. So 3 features common. If you think in terms of their social security numbers, nothing in common because they're 2 unique numbers. Okay? Now, what I'm basically interested in here is that I have this I have these techniques for computing the value functions for the state spaces. That's what we did in the last 2 classes. But the problem is the state spaces can be very, very large. So there should be a way of representing the value function in a compressed format, so that it won't take an array of size. If the number of states is trillion, then you don't need an array of size trillion. There should be some formula that will right away tell you, for each state, you put its features into this formula, it will tell you the value. Do you see what I'm saying? That's compression. So you want something like that if you want to deal with large state spaces. So examples of compressions are all over the place. For example, JPEG is a compression algorithm, right? And zip is a compression algorithm. Okay? So keep that part in mind. The second part is, it's not just that you want to keep things compressed. The other problem of having very large number of states is the approaches that you have, the TD learning, the Q learning, etc., will take forever to converge. It's impossible for them to have experienced so many different state-state transitions to have figured out the value of every state. You understand what I'm saying? So TD learning, for any transition, it needs to occur infinitely often for the TD learning to figure out what the value is. And a whole number of these transitions have to occur so that everybody's value converges. In theory, it is possible. But in practice, there is not enough life. You don't live long enough. You don't have enough computing power. You don't have any of these things. Most importantly, you don't have enough examples. Examples being the state transitions. So you want to be able to quickly, having seen one state transition, be able to say, oh wow, okay, then I am trying to make these guys, so I was in S1, I transitioned to S2, and using, for example, temporal deference learning, I will now say the value of S1 will be nudged a little closer towards the value of S2. Right? That was the whole point of temporal deference learning. Do you guys remember that? That's what we were doing. In the past, what we would do is we will essentially just nudge it by actually changing the number stored in that cell. If it was stored as 14, and in fact the neighbor is 95, then you will nudge it towards 95, so it will be like 19 instead of 14. But now actually, so you have one of two options. One is you're storing all the values in a compressed format. So you can uncompress them, and you have the numbers, and then do the update, and then recompress them. That is possible. If only thing that you cared about is compression, then that's what you would do. But as I said, the second reason why you are interested in how to deal with large state spaces is, with a few number of examples, you want to be able to learn something about the value, not just of this state, which transitioned to this other state, but all states similar to it. Do you see what I'm saying? So, in fact, an example that happens here is in terms of the Pacman example. Suppose you sort of learn something about this state. You all know that this state sort of looks very similar to this state and looks similar to this state. Does your program know that? No. So if you're doing atomic updates in terms of TD learning, then whatever you learn here will not apply here, will not apply here. You're strictly saying, I have not seen that. Do you see what I'm saying? You're not going to say it. And so basically, however, you can see that if you think of these in terms of what you consider features, for example, features like distance to the closest ghost, distance to the closest dot, the number of ghosts, and then is the Pacman in tunnel, etc., etc. These features are not that different from the kind of features we were talking about earlier. Saying, is the person awake? Is the student awake? Is the student having a long hair? Is the student paying attention? Does the student have high homework grades? Those are features too. Do you see what I'm saying? So if these features, if you represent these states in terms of these features, then essentially you have a factored or feature-based or lifted representation. When you do that, whatever you learn about one state sort of transfers to all the related states, where the states are related in terms of features. If you learned that all 6 feet tall people who have 95 in the second homework are historically getting A+ grades in the class, then, whoever, if you find some 6 feet tall, 95% grade homework or 2% in your class, you know that they're going to get A+. Or also you can do social engineering. You can try to make yourself 6 feet tall and get 95 in the homework too, and see if that will happen. You see what I'm saying? None of which you could do before when everything was in terms of social security numbers. Again, much of this, you guys understand this in the back of your head, but I'm sort of trying to bring it up, saying that learning is not possible unless you have feature-based representations. Learning in the sense of generalization is not possible unless you have feature-based representations. Okay. So basically the reason we want to do this kind of learning in the context of reinforcement learning is there is never enough training data and learning takes too long, plus storage issue. Even if you have enough memory, these other two problems exist. So because of which you want to be able to represent these states in terms of their features. And then going back to this point where I said V of S1, let's say, is 17, and it transitioned to a state which has 95 value in one particular experience. If you are an atomic representation, you would have made this 17 to be 90. If you are in this feature-based representation, then you need to somehow, there was some formula for converting features into value before. A simple idea that we will look at first, because straight lines seem to be working in most of the cases, we'll assume that there is some linear function of features. W1 times F1 plus W2 times F2 plus W3 times F3 plus Wk times Fk, where there are k number of features, and I'm multiplying each of the features in by some weight, adding them all up. That's complete linear way of connecting features. I'll just assume this is going to be a good fit for the actual value function. And you might say, are you drunk? And then I'll say, were you drunk when you tried to put a straight line through those points? No, we are equally drunk. You see what I'm saying? We try basically the straight line assumption, we can see how far it goes. And then start saying, oh, linearity assumptions are not working, we'll start doing some non-linear stuff. Okay, but linearity assumptions actually work large enough number of times that people always try to use linearity first. So in this particular case, imagine you did do linearity assumption, then so basic idea is instead of using a large table to represent VRQ, you're using some kind of a parameterized function. As I mentioned, the parameterized function. The parameterized function. Yeah, as I mentioned, the parameterized function for me is of the form W1 times F1 plus W2 times F2 plus etc. Wk times Fk. Given a state, I know the Fi values. All I need to do is to find the weights such that that particular sum actually corresponds to the true value of the state. Yes?
So what is the guarantee that we can actually convert that atomic state to a non-atomic state?
You can always guarantee. How did I convert you guys? You are obviously human with infinite skills, etc., etc. I just said, this guy has a beard and he's looking brown and has dark hair. Those are the only features I've decided to use.
What's the better
if I take more features about you, that will be better. Or I could just say everybody is different. In which case I'll take your social grade number. At which point then I will not know anything about students at all. Everybody is a new social grade number. So let me learn about your life story. You see what I'm saying? This looks like a beautiful thing to say in a sociology class. I don't make any presumptions about people. Are you kidding me? You of course make presumptions about people. Otherwise you won't be around here. It's just some kinds of presumptions are considered bad. Do you understand what I'm saying? Okay. Anyway, so it's a very good question. When you are going from states to features, representations, who is coming up with these feature representations? There are actually two answers. The old idea is humans who might know something about that problem will suggest to you the features. For example, in the example that we saw here, these things, I'm appealing to your intuition. Right? I'm saying, yeah, these things seem to be kind of some of them, let's throw them and see what happens. You see what I'm saying? That is basically, I'm using my understanding, a little bit of my understanding about this problem to say these kinds of features might make sense. So in the case of chess, for example, remember the chess evaluation functions? Those had features too. The number of pawns on the board, okay, and the number of kings on the board, number of queens on the board, number of knights on the board, etc., etc. Those are the features. Now, you could, just a second, you could also have used extra features such as the color of the shirt of the first player playing the game, the color of the shirt of the second player playing the game, the shoe size of the first player, the shoe size of the second player. Do you see where I'm going? I can make infinitely more features. You don't do them because you know, somehow you know how chess works and you think chess doesn't depend on the shoe color. Little do you know. In fact, chess completely depends on the shoe color. Maybe, you never know. Okay, if you don't know anything about chess, you have to consider everything depends on everything. Remember, we thought black cats decide our fate. If you see a black cat, you would fall under a, passing bullock cart. In those days, there were no cars. Okay, if you're still worried about black cats, God help you again. Okay, so basically, you just went with that sort of assumptions in terms of what are relevant features, what are irrelevant features. These are fundamental questions. So the second idea, and I have two questions I will get back to. The second idea is instead of asking people to give it, you can say, I will basically take a picture of the world that I'm seeing. And then let's sort of let the learning system figure out from the picture what pixels in this picture seem to matter, what pixels in this picture don't seem to matter. If the concept you're trying to learn is what is a cat and what is a dog, those are classic tacit knowledge problems. If you ask people to tell you what should you be looking for, they don't know exactly what you should be looking for in the image. In those cases, you may as well just go from the image pixels. If on the other hand, you are in this world, unless you have some kind of a masochism built in and you don't want to ask anybody, and you think there's some extra points for rediscovering the wheel every other day, you won't be looking at images to directly go to the values. And yet, come to the party, deep reinforcement learning systems, most of them, the ones that you keep seeing, including those multi-agent systems that supposedly hide and seek, they're all famous mostly because these guys are essentially saying that if you have enough data, there may be some way of finding some functions of these pixels which are connected to their representation. So this is the reason why, in fact, the deep learning people call themselves the representation learning people. The main conference on deep learning of late, other than NeurIPS, is ICLR, is International Conference on Learning Representations. The strange part is they learn representations that make sense to them. They don't make sense to you at all. You see what I'm saying? When I showed you these representations, they made sense to you. Whatever representations the neural network learns when it is going from pixels to some classification task, you don't understand what it basically is thinking of in its own mind. That's the whole reason why this whole entire cottage industry of explainable AI. Because you're doing something, sometimes you're winning, sometimes you're losing. How the heck am I supposed to trust you? Because I don't understand your vocabulary of features. You touch a small thing, the entire thing moves. Now the next question. What was your question?
My question was that, so you were talking about how there's like a feature-based representation of functional information process.
No, functional approximation is possible only because you have feature-based representation.
Isn't this all turned into basically doesn't everything boil down to a functional approximation?
No, that's my point. If you are around last few classes, I assume you were, you realize you could do reinforcement learning without any kind of functional approximation. If you say that, is there something that you can say as a shortcut for generalization? Yes, functional approximation is generalization. There is a question there, yes.
So can you say that feature selection can increase bias?
Okay, again, what's the word bias supposed to stand for? Bias in the good way that if you don't have bias, you die? Or bias in the bad way, in the sense if I say you are biased, you'll feel very sad and ashamed.
In a good way.
Good way. So every feature selection is essentially introducing your prior knowledge about what matters and what doesn't matter in the world. And so it is a bias. Completely right. You see what I'm saying? The reason they did not put here Pac-Man is yellow or not, which is like the most important thing about Pac-Man. I mean, who cares about anything else? I mean, when you see Pac-Man, you see yellow is blaring down. There is no feature about yellowness. Because apparently these bozos played Pac-Man for long enough time and realized the color doesn't seem to matter. Can I not make a Pac-Man where color matters? Of course I can. I can make new games with new rules. So if I don't know anything about the game, I should assume everything can be possibly mattering. In fact, the time the sun got up that day, sunrise time on that day, might also matter. Everything can matter if you have no idea how anything is connected to anything. And so, in selecting certain features to represent the state, you are perfectly right. You are providing background knowledge about the problem, and you are sort of putting a bias. Okay? Any other questions? Okay. So what I'm trying to do at this point, of course, is, so instead of using a large table to represent this, I want to represent this. The number of parameters should be sort of small enough compared to the number of states. Okay, which is what we are thinking because it's supposed to help compress. Okay, and then you want to somehow get these parameters from experience, and that is basically curve fitting. If I give you points, then you come up with a straight line equation which such that that straight line passes through all those points. You see what I'm saying? If I give you a whole bunch of points and you will come up with y equal to mx plus c, and m and c are the weights. Y is what you're trying to predict, x is the only feature. If it's a multi-dimensional function, then x1 all the way up to x100 are the inputs, and you're trying to predict y. And so it will be, if you're looking for linear, then it will be y equal to m plus, m1 x1 plus m2 x2 plus mk xk plus c, which is basically what we're looking at. So we're trying to look for, if there is like the values of all these states are represented in a k-dimensional feature space. I'm trying to look for some sort of a hyperplane, some sort of a line that is going through all these points in this k-dimensional hyperplane, such that the line is in some sense, is the best line. You see what I'm saying? In some sense, the best line. So that brings us to the next question. What is the best line? What is the best line? And in fact, what is the best hypothesis? Consider the following thing. Here's the example. You guys see this? Should I be looking for a straight line or something else? If I look for a straight line, notice that this poor guy will be unhappy because the line won't pass through them. Do you see that? And he says, you are noise. Right? Okay? So, here's my question. In fact, if on the other hand, instead of looking for lines in the same example, you looked for, let's say, a 20th order polynomial. For that same example, then I would basically have a 20th order polynomial which looks like this. Everybody is happy. Everybody in the original training data is happy because the hypothesis goes through all of them. Which is better? As a lossless compression, which is better? Imagine I come up with a non-loser JPEG, which basically compresses all the pictures that include you, but you won't be there. I compress you out of the picture. And then I'll just say, like your mom says 25 years later that, we used the state-of-the-art technology that Wow was selling, and it was, compression technology. What can I do? You would be very unhappy. Because compression is supposed to be lossless. Especially entire people moving on the picture is no good. I mean, there's a really nice way of compressing pictures, which is cut them into really small piece. Just my head in the entire big picture and store that. That's a lossy compression. Okay? But in general, when you are thinking about generalization, you have to understand that generalization has both the idea of compression and the idea of predicting unseen examples. And it is very important not to get stuck in predicting only, in only compressing the training examples. Because in fact what happens is, the reason you think this is correct, this is wrong for generalization is because you think additional points that come further are more likely to be on this line than likely to be on this Widley 25th order polynomial. Now, how did you decide this? This is just your gut feeling, your bias. Do you see what I'm saying? Okay? So in general, and of course you can check whether this is true or not by essentially testing this hypothesis on various kinds of examples with held out data sets and see if in fact this is winding up being true or not. And oftentimes it actually winds up being true. And in general, this particular thing is being known as multiple different names. One is called the overfitting. A compression essentially makes sure, a lossless compression makes sure that the function must pass through all the original data points as closely as possible. It should fit. But what you're saying is if what you're interested in is generalization, and if in fact the data can have noise, then if you try to ensure everybody fits, then you might be overfitting. You are fitting your curve to the noise in the data. Part of generalization is to be able to look beyond the noise. Do you see what I'm saying? So this is overfitting. And it's also, a more technical term is what's called bias variance trade-off. From statistics, this other term comes. And one way of thinking about them is if you consider different kinds of hypotheses, zeroth order polynomial, first order polynomial, second order polynomial, 29th order polynomial, and so on. The best 29th order polynomial, best second order polynomial, etc. Given the same data, here I'm trying to fit the best 15th order polynomial here. As you increase the degree of the polynomial, you have to be able to see that the fit to the data would be more and more and more perfect. Right? Because if you have 25th order polynomials, that includes every other polynomial up to degree 25th. Right? You just make sum of the coefficient 0, then you can get second order polynomial when you're looking for 25th order polynomials. It's just a 25th order polynomial with many coefficients here. So you're looking for superset of the hypothesis, you can't go wrong in terms of compression. So in fact, the error in the fit to the training data sort of monotonically reduces. And yet what you are telling me between this and this is if you also draw a different curve, there is a whole bunch of test examples, the tests that haven't been seen yet. And I just basically use the test example to check how good your learning is. And don't tell you at all how good your learning is, but I just remember how good your learning is. And then if I plot that, it looks more or less like this. In the beginning, it tends to come down, but as you increase the expressiveness of the hypothesis, it's basically you're considering 25th order polynomial, then it started overfitting to the noise. Okay, and so in fact, the test data, which may not have the same exact kind of noise, will be wrongly fitted or wrongly classified. This is one of the fundamental curves of generalization. This is bias variance trade-off. This is overfitting. Okay, and in general, this idea that you have that, in fact, the previous one we part of that, you want to sort of look for the number of parameters to be small compared to the number of states, which essentially means if there are 10,000 states, the number of parameters is sort of connected to the number of features and the degree of the polynomial, if you're looking only at the polynomials. Right? So if you have 10,000 feature states, you are looking for number of features that are maybe 100, hopefully. Not 10,000 features for 10,000 states. Because if you have 10,000 features and 10,000 states, that's almost like having, you actually allow for each state to be completely different from the other. Right? Okay? And the other thing, of course, is, so the number of parameters are small, and then of course you also look for the smaller, look for straight lines before looking for curves. This is bedrock of generalization. Unfortunately, right now, as things are going on, when we get to neural networks, we will find that people are scratching their heads pretty hard because multiple times you would wind up fitting, a neural network can be thought of as a high order polynomial of some sort. You can think of it as a huge function with many, many coefficients. Every weight in the neural network. We haven't talked about it here already, but some of you know that neural networks have weights. We'll talk about it by end of today or tomorrow, or next class. Okay. So this number of weights essentially are the parameters that you have to learn. Many working neural networks these days have more parameters than there is data. So I just told you beautiful theory, and I also told you we have no idea what's going on right now. Do you see what I'm saying? Mostly, in fact, overfitting is a bad idea. Mostly people realize overfitting will happen if you have more parameters. Mostly people seem to think that somehow it is not happening in neural networks. Mostly people could be wrong in thinking that overfitting is not happening. And in fact, we will get to a thing called adversarial examples, which will make us realize that there may well be huge amounts of overfitting